Have you ever wanted a tool that could instantly give you all the nutritional information you need to know about your food? In this video, I'll be presenting the project I did that utilizes both edge and cloud computing to perform food composition identification. The main aim of this project is to allow users to simply take a picture of their meal and use the application to analyze and estimate its nutritional composition. This includes key information such as calories, proteins, fats, and other important nutrients. This makes the process much more convenient and accessible. It also provides information that's specific to what the user is about to eat, rather than just giving general nutritional information found on the internet. Users will also not have to compare different online sources to get an accurate estimate. Moving on, we have an overview of the project that I did. The IoT device used is an Android smartphone, but I used a simulation of it in Android Studios for testing purposes. Additionally, for the edge computing component of my project, I made use of a TensorFlow light model that is directly embedded into my Android application. This model is meant to do the first round of identification and estimation. However, in the case that this light model is unable to identify the food present in the picture, this is where the cloud computing component comes in. On a cloud server, in this case Azure, I hosted a larger model that has better accuracy in this food classification task. Finally, as both these AI models are only meant for food classification, I also created a backend server that makes use of an API to get the nutritional composition of the food. Now, I would like to go into more detail on how each of these components were built. For the AI model, I made use of Azure Custom Vision, which has its own domain for food classification. Using the Food 101 dataset from Hugging Face, I trained both a light and heavy model on Azure Custom Vision. The light model is trained with 25 images across 50 categories, while the heavy model is trained with 50 images across 50 categories. From the training results, we can see that the heavy model has better performance, with the trade-off of being much larger. The heavy model is queried through its prediction URL. However, the light model is exported as a TensorFlow Lite file to be embedded directly into our application. Next, I set up the backend server that handles the communication between the Android application and the other components. However, to make sure this backend server isn't just accessible locally, I first created an Azure virtual machine to host the server as shown. After I SSH into the virtual machine, Green Unicorn is used to run the server so that multiple users can access it at the same time. It spawns multiple worker processes, so several requests can be handled simultaneously. This is what allows multiple Android devices to hit the server at the same time. Over here, we have the Flask application that we have set up as the server. First, we have the classification part, where the server sends the image to Azure Custom Vision model hosted on its own cloud server. We also set up another API call to get the nutritional information from a public API set up by the United States Department of Agriculture, which covers a wide range of food options. Moving on, I use Android Studios to build my mobile application. This is how the application looks like, with the homepage allowing the user to either take a picture of their food directly or choose the picture from their gallery. Next, the user can then send the picture that they have chosen to the embedded model first to get the preliminary results. In this case, we can see that the model was able to successfully classify the food in the picture and got back the required nutritional information. However, in the case where the edge model is unable to identify the food correctly, the user can choose to use the model hosted on the cloud server instead, which often does give better results. This is done by sending a request to the backend server through its public IP address, which then sends its own request to the cloud server hosting our heavier AI model. For example, we can see over here that when we try to get the edge model to classify this salad, it actually wrongly classifies it as deviled eggs and also gives the wrong nutritional information. The user then has the option to ask the class model, and as you can see, the class model is able to correctly identify the food in the picture and return the correct nutritional information. Additionally, if the results with the cloud model still has a low confidence, like this picture of lasagna shown here, the user can submit the photo along with their own label to the backend server to save. As you can see here, over on the virtual machine where we host our backend server, we have a feedback images folder. This folder contains all the submitted photos along with their corresponding labels. The admin can then vet through these submitted photos and labels and verify their accuracy. Afterwards, they can be uploaded to the custom vision dataset. This is done with this retrain.py file. After being uploaded to the custom vision dataset, the model can then be retrained and include the images that they have missed out before. Finally, we can see that when we have multiple devices accessing the same server, there is minimal delay in communication because we implemented Green Unicorn earlier. This can be seen by the nutritional facts being returned around roughly the same time. To conclude, this project made use of edge and cloud computing to create an efficient Android application for food nutrition analysis. The next step to this project could be a separate AI model that's also able to estimate the mass of the food present in the picture. With that, thank you for your attention.